It is the appointed hour. This is session E22, Robust Structures. My name is Radar Buerhovde from the Buerhovde Group in Tucson, Arizona, where the sun shines always. So this is a very hot topic today, robust structures, structural integrity, and we have two very fine, very key people in that whole area of study and engineering exploration that will be with us this morning and share with you their expertise. So you won't be listening to very much. I intend to make very short introductions so you can hear the speakers that you are here to listen to. Our first speaker is Professor Chris Foley from Marquette University in Milwaukee, Wisconsin. And as you can see, his presentation will address the issue of characteristics of robust structures. Chris?
Thank you, Radar. It's nice of you all to get up early in the morning today and with the rain, get going bright and early. I'd like to thank Radar for putting the session together. I think it's going to be very interesting. Kirk also for participating in the session. I think that it's going to be quite interesting as well as hopefully thought-provoking, because this area is certainly evolving very rapidly worldwide, and I think there's going to be a lot of good information related to the understanding of structural systems that comes out of the efforts that we're putting forward, at least these days and today. Now, predicting what might happen to a structural system during its service life is pretty tricky for structural engineers. It's not something we can do at a drop of a hat or fully understand very, very quickly. The buildings that you see on the left, well, maybe you don't see them on the left. There we go. Sorry about that. The buildings that you see on the left are essentially, obviously, looks like a terrorist attack, and that's essentially what they were. Unfortunately, the New York City building that you see there was a suicide. Okay, hard to predict that. Certainly a design load that results from that is difficult to predict. The Chicago building that you see is a vehicle impact on a corner column. Naturally, there is a portion of the structure that collapsed. The London, UK building that you see there is a gas explosion, and most of the stories up above landed on top of the structure itself. Some damage in the street as well. Now, it's nearly impossible to quantify all these scenarios as you begin the design process and begin moving forward. However, there is one thing that is clear. Many, many structures can suffer significant damage without progressive collapse, without disproportionate collapse. Why? That is a big question that we need to take a look at and understand. Now, as you look at it, I'm sure Kirk is going to have much better activities and experiments related to this, which will make it quite exciting to be able to sit in the audience and watch some of those and look at some of those. But some tests that were sponsored by AISC to understand the damage that results from blast loading have obviously been done. And here's a clad column case that you see here. And the testing that has been done demonstrates that the structure can be a fairly tough system. It can undergo some rather large ductile response and ductile deformations without significant damage. Now, the objectives, at least for today, are unfortunately manyfold, but at the same time, fortunately, we can talk about a lot as well, is to, number one, develop an attempt at defining what robustness means. It's not something that's a term that is easily defined. It's very broad, very overarching in terms of a statement that it can make. Now, we also like to look at quantifying the roles of flexural collapse mechanisms as well as geometric stiffness mechanisms in robust response and the characteristics of the structure. We'd also like to start illustrating some behavioral characteristics of multi-story systems so that we can begin to quantify whether or not a structure is robust. And we'd like to illustrate the role of one-way and two-way catenary membrane action that might exist in the floor slab system and the grillage of steel framing that is beneath there to help understand this, and then give a brief overview of some connection testing that we've done at MSOE and Marquette to get some idea of what's going on with simple connections in a catenary or slinging mode, if you will. And we'll begin our discussion by looking at how we might define robustness. And that I thought was key to do first off, try to make a definition here. Now, there are a variety of definitions. Unfortunately, Merriam-Webster going straight to the dictionary is what everybody on the street might think of when you talk about robustness. Beebe in 1999 is a UK researcher, a lot of research in Europe going on currently as well as here in the United States. Beebe began thinking about progressive and disproportionate collapse from a reliability basis many years ago now, over a decade. or nearly a decade, I should say. The GSA is naturally the General Services Administration, and there are definitions there as well. Now, all of these definitions leave a lot to our imagination. That's both good and bad. We as structural engineers need to quantify in order to design. And some of these definitions of robustness aren't totally quantified at this point in time. And with more complex structural systems that we generate, understanding when a system is going to be robust becomes more difficult. Now, as I began thinking about trying to develop or entertain the notion of integrity provisions for steel structures, we need to ask some questions and we need to pursue some answers to those questions. The first one is, what does the structural steel system get out of the box? You do nothing special. What does the system have in terms of robustness? The next thing is, can these inherent transfer mechanisms be enhanced? Can they be quantified? The next thing, there are horizontal and vertical ties orthogonally laid out in a steel building. That's how we build them in many cases. What are they good for? What can they do? We need to figure that out. Ductility is likely the controlling limit state of all behavior. You have to have large deformations to get the belt flexural mechanism and the suspenders catenary or geometric stiffness. What do you have in terms of ductility demand? The last thing, what force demands might be present in the system after damage occurs? A lot of focus is being placed on what causes the damage. I've tended to think about what happens after some damage happens, whatever it might be. And then the main benefit to answering all these questions is we may have the foundation now for ACI 318-like general structural integrity provisions for steel structures. Something as simple as 3 bolts per connection minimum, 2 bolts per connection minimum, etc. Now, in terms of defining robustness, again, trying to get at the heart of quantifying what robustness means, you can go through and look at performance-based engineering type definitions. And the first definition that you see here is really an extension of the NIST thinking. And in this particular case, you may have a hazard, which might be an unintended loading, could be a malicious act, could be seismic loading, could be human error during design and construction. You have limit states, which classically might be a deformation limit state, interstory drift, could be connection plastic rotation demand. You have damage, and in the FEMA world, with the earthquake engineering community, it might be something like none, slight, moderate, complete, just to begin to attach some meaning to these terms. And then you have scenarios of loss, and that naturally might be direct loss, could be injuries or death. It could also be indirect losses, like lost opportunity, lost rent, loss of function. All these can go into defining loss. Now, unfortunately, there's a large range of possibilities for hazards, limit states, etc., and that needs to be defined and can be difficult. Now, robust can also be defined as an acceptable probability of collapse. Now, in this avenue, I tend to have a little more feeling for it, and that's why I selected another alternate definition of this. Again, you may have a scenario that could be malicious attack. Again, could be error during construction or design. The local damage scenarios, everything tends to condense a bit here and become streamlined. It could be damage to a column. It could be damage to a girder. A lot of the provisions and procedures that we use now to assess the tendency for disproportionate collapse involve removing a column, damaging a beam, etc. Well, now you can begin to connect that to probabilities of collapse, which allows you to define an acceptable probability of collapse, which allows you to put a threshold on a robustness value. So there's an awful lot behind the scenes that we can't talk about today, but somebody's going to have to begin filling these in, and that's important. Last but not least, down here, part of my life is spent developing optimal design algorithms for steel building systems. You can also look at expected costs, and you can begin optimizing a design for a level of robustness, and that's something that we might do in the future. Now, the UK, Eurocode, European groups are beginning to look at risk consequence on this basis. And this process allows you to look at high risk, high consequence, low risk, low consequence scenarios and events. Now, the problem with formulations of this nature, and it's a stab, it's discussionary at this point, but these parameters that you see along here help you to define a risk factor. If your structure has a higher risk factor, you might need to investigate some more advanced design methods to make sure that you're going to satisfy that need to mitigate that risk. So those load parameters that you see down along the bottom and the side are difficult to define. The C values that you see are a load parameter. That's the likelihood that the system is going to be occupied to a large extent after an event. And then you have some structural parameters, which is the classic, what degree of load distribution might you expect in the structural system. You then have E, which is an environmental parameter. That's a way that you can figure out what the tendency for collateral damage is after an event. And then you have some parameters characterizing the likelihood of injuries or death, N. And then you have some societal parameters, meaning how does society feel about this structural system undergoing a collapse extent that you're willing to design in or you're allowed to design in. Now, structures can be rendered robust without intervention if some risk factors can be established and decided upon. Now, that leads us to the following kind of pausing point, if you will, and we have some overall view on what robust might mean, and we have three ways that we can define it: an acceptable probability of loss, an acceptable probability of collapse, or an acceptable probability of risk and consequence. And those are, again, they're still rather high-level terms and concepts, but at least it has an ability to put some numbers and have the rubber meet the road, as they say. Now, robust structures, however, are redundant. That's interweaved throughout all of these concepts that you see. There's reliable levels of ductility that are needed, and we need to figure out what those are. And there needs to be an ability to accommodate load reversals during events. And that's really how we're going to begin our discussion of characteristics of robust response, all within these frameworks of redundancy, ductility, and the ability to have load reversals accommodated. Now, I'm not going to get highly equation-oriented here, but I at least wanted to point out some simpler ways where you can begin to quantify and characterize the robustness of a system. But first and foremost, there are two primary mechanisms that are going to be activated in a structure that has some level of damage. The first is going to be a flexural mechanism. And the terms are broken up here according to the plastic moment capacity and span length. We have an interior column. Again, people can argue all the time that this is the wrong damage model, but there are many damage models. But we have an independent span system that becomes a continuous two-span system after some damaging event. Some flexural mechanism occurs, some geometric stiffness mechanism occurs. Now, I'm not calling it catenary. Catenary has the connotation of a parabolic distribution in shape. That's not necessarily what's going to happen in a steel structure. So we'll talk about geometric stiffness. That's the thing that's going to be activated as deformations increase. Now, there's a huge assumption here that you can undergo plastic rotation demand at very large deformations. Now, the plastic design methods of the 70s were not really a second-order type formulation. They evolved into one, but the deformations here are quite large, and we need to have the rotational demand undertaken, if you will, with rather large deformation and horizontal forces. So those big assumptions are there. Now, we can begin to look at partial end restraint on the connections. We, as steel engineers and designers, have a luxury. We can go through and tweak some of the connection stiffness parameters. We can tweak the connection strengths as we go along. And as we look at the partial end restraint, we can isolate moment capacity with a term beta and stiffness relative to the flexural rigidity of the spans that are generated. And as you look at this, we still have the same big assumption. Can you undergo plastic rotation demand under large deformations with significant horizontal forces? Now, when alpha theta, and that's really the stiffness parameter, begins to vary from 20 to 2.5, these essentially are fully restrained connections. These are flexible connections. As you look at these curves, all of them achieve essentially the same flexural limit state. Okay, it's a plastic mechanism. The only difference is really nothing among all the shapes other than how you set beta. And in this case, we're taking it to be full strength, beta is 1. Now, as you begin to change the connection stiffness parameter, you begin to allow larger and larger deformation to take place in the system. You're still going to have the same flexural moment capacity, right? You haven't changed that. You're just changing the stiffness of the connection. Now, one can argue those are intimately linked, and they certainly are, and we'll look at that case in a moment. But what you're doing is you're accumulating vertical deformation very rapidly. Unfortunately, the structure is not smart enough to understand that it should omit its geometric stiffness. It's there. So what happens is, as this vertical deformation is occurring because the flexural mechanism is giving up the ghost, you've got geometric stiffness kicking in and generating large horizontal forces. So you can't have the free lunch, as they say. They both come together. Now, it's a very important interaction as they go along here as well. Now, what level of these horizontal forces exist? They can be quite large. And in testing, you see quite large horizontal forces. But the systems are quite tough, too, and they're able to carry these forces. Now, what you see here is the flexural connection stiffnesses are reduced. Again, these vertical deformations tend to increase quite rapidly. And what you see here in the vertical displacement is you get some indication of that. Now, these may be, as you might say, illustrative only in terms of their variation. But again, we're trying to look at the characteristics of the system, and we can take some liberties in how we value or vary these parameters. Now, as you go through and have a flexural mechanism giving up the ghost quickly, you end up generating horizontal reactions in these systems very rapidly as well. So what we can take away from some of these curves is that when partially restrained connections are being utilized, you are going to have a situation where you're going to activate geometric stiffness very early in the system's response to that damaging event. As a result of that, the geometric stiffness, if the forces can be carried, will be generated very rapidly. Now, what this means indirectly now is that you might have a higher tendency for tensile rupture at the connections if those forces can't be accommodated along with these other demands that are being placed on the system and on the components. Now, we can begin to relax some of our connection scenarios a little further. Now, some might have noticed that previous slide and said, what connections at the end of a two-span system are infinitely stiff and axial behavior? Well, the answer is none. Okay? So now we start to manipulate that term. Now, I would counter a bit and say, okay, what building system has I've got to be a little careful. What building system has a floor slab removed so that it's not going to contribute in-plane shear stiffness, which may also contribute to restraint at the ends of the span? So there's a couple of things going on there that we need to look at. So experimenting with some of these stiffnesses gives us an indication of what's happening during the system in a qualitative sense. Now, what you see in the curve here is this top green curve is essentially a partial strength, partial stiffness end connection. Now, the connections that you see out here, there's a little bit of error introduced because there's no axial springs that you see in the middle here. But in reality, everything's being controlled by the strength and stiffness of what's out here. So the deformations are going to be a little different, and we can argue about that after the presentation as well. But nonetheless, what we're doing is we're looking at the response of the system as these stiffnesses vary, the axial stiffness that is. And when you have a partially restrained connection, because the vertical deformations are tending to increase very rapidly, geometric stiffness is therefore generating forces very rapidly, you have a higher sensitivity to end restraint axially in a partially restrained connection sense versus the fully restrained moment sense. So there's a little bit of insensitivity in that case. Now, it's tough to run away from this saying that FR connections are more robust than PR connections, but to be quite honest with you, we don't fully understand both under this kind of response, and it may find out that things tend to more or less equalize out, and some testing on simple connections indicates there's an awful lot of robustness in those systems as we move forward. Now, what happens when you get more than one beam? Right? We have stories. There are philosophies that suggest you should harden a floor level and carry everything up above. I'm of the opinion you might want to let the structure react to the damage as it wants to, unless it can't. So let it figure out what it needs to do first, and then if you need to help it, help it. Now, what you see here is a very, very simple system. 3 horizontal beams assume that something happened down here to a supporting column. And what these central columns do within the system is they facilitate a more or less compatibility of deformation between this level, and this level. So now what you're doing is locking 3 floors together. And there's a notion that you cannot superimpose inelastic response because inelastic is nonlinear. Well, in reality, that's true. You're not going to trace the response actively or accurately, but the strength of the system can be superimposed. And that allows us to do some very simple calculations to come up with some very quick answers as to what the characteristics of the robust system might be. So the 3 cases that you see here are manipulations of the loads at each level. So I'm trying to figure out how the systems respond together to resist the loss of that lower story column. Now, you still get geometric stiffness effects kicking in. These are huge horizontal forces, but don't let them scare you. Okay, tests show that some of these forces can be carried. We wouldn't believe it, but again, we tell the structure a lot of what it doesn't know. So we want to make sure that we can address that later on. Now, the total loading that you see at the flexural mechanism formation, meaning you get plastic hinges at each one of these locations for each floor level, indicate that all three systems carry more or less the same loading. And what I'm doing here is trying to predict that capacity by doing nothing more than superimposing the mechanism capacities. And we know how to do that and how to calculate that. Now, unfortunately, as well, what you get here, I said these large horizontal forces, they're rather consistent throughout all levels at all load case scenarios. And you see for case A that you generate this catenary or geometric stiffness response right after the flexural mechanism forms. So this is a plastic analysis type response. This is a geometric stiffness response, and they are linked to one another. Now, it suggests that a more robust system will have the ability to tie multiple levels together and make sure that they're going to be dragged along for the ride. Right? You want everybody to work according to their strength, and that's what's happening with that central column. Now, what happens when you have a building and not these isolated walls within the structural system? How do you begin to simulate the response of the system now, which involves more than one beam, two beams, three columns, etc.? Now, here's a scenario where we looked at a three-story building, modified slightly from the research that SAC had done, and we went through and looked at three-dimensional transient inelastic response of the system with infill beams that were pinned and with perimeter moment-resisting frames. Now, the first thing people should jump on this slide is, why didn't you pull the corner column? Well, yes, very important. I'll move on. I won't argue. The interior column locations at the perimeter moment-resisting frame is what we're at least focused on right now. Future stuff is going to have to start looking at those scenarios. Now, I would counter the corner column. If you're going to study removal of that corner column, you best not be forgetting about the orthogonal framing contributing to that response. Okay? So no two-dimensional analysis. You're being far too conservative in what you're doing. Now, the floor diaphragm stiffness was attempted to be modeled here using weightless X-bracing members. So somehow we would like to see what a floor diaphragm might do to alleviating or perhaps enhancing the tensile forces that are generated in the connections in that moment-resisting frame. And that's an important aspect, I think, to the structural analysis. There was a simplified interaction of axial load moment, mainly as a result of some software limitations. And then the local damage scenario that you see involves removing one of these columns down below. And we'll focus on one of those now. Now, as we walk through the analysis, how was this done? Well, we wanted to look at the transient response. So as we loaded this structural system, essentially we put gravity loading on, and I can explain what the magnitudes of the loads were. And then at the same time we applied the gravity loads, we applied the column loading to resist it. So we grew that column loading with a time history function, and then after we let the system stabilize with its inherent damping, we turned it off. And we watched what happened within the system. And the system now responds at all three levels in some unique ways. And what those diaphragms also allow you to do is they allow you to explore what's happening throughout the floor plate as the system responds to that damaging event. So what you see in the X-bracing members, admittedly a simplistic model, but you begin to see how the diaphragm itself has both compression struts and tension diagonals or principal tension diagonals throughout that floor plate system, and they're all helping and working to resist the loading. And that's what we wanted to try to do, is figure out how that might happen and how we might begin to quantify that. Now, it also suggests, and the analysis suggests, that these horizontal deck systems, if you will, or in-plane shear stiffnesses, should be considered as potential tying forces. Right? They're there, and if we can quantify what their contribution is, we might be able to alleviate some of what we're expecting these horizontal members to carry. And that's an important thing. Now, as you begin to look at the individual components within the system, you begin to look at scenarios where strong column, weak beam behavior, that's another characteristic that it appears favorable, and people have known this for some time, but you end up getting a capping of the bending moment demand that's being funneled into a column. And that we've known to be important in seismic analysis, and it certainly is important here, and we might have expected that. It's a good thing to have happen. And if you look at the results, the inelastic response will likely need to be used to assess the system's strength and characteristics. So elastic analysis isn't going to fly here. So if you're not comfortable doing inelastic analysis and comfortable understanding how a software package is operating in an inelastic analysis sense, then unfortunately you may have to get comfortable quickly because it's going to be needed. Now, column 268 or beam 268 gives us some indication of what's happening. From a design point of view, you'll have a full plastic moment generation under gravity loading, and you will get a full reversal of moment. Okay? So that full rotational demand at the plastic moment level is going to have to occur along with some significant tension forces. Now, how do you develop a protocol like the FEMA group did for earthquakes? They studied many ground motions, they looked at the demands on connections, they developed protocols for loadings that had energy dissipation characteristics, etc. We now can do something similar to that here if we understand the response. So now we'll have some gauge on how we could do connection tests to demonstrate that things are going to move forward correctly. So in the analysis of the three-dimensional system that we saw, strong column, weak beam behavior is going to help. Corley pointed this out after the Murrah Federal Building with that research group. We also have the ability and need now to undergo full plastic moment rotation along with significant axial force. Now in these three-story frames, it was about 2% of the yield strength of the member. That could be on the order of 20, and you saw previous systems here, 75, 80, 100 kips. We need to figure out if the connections can carry that. Now, perhaps the most important thing that we neglect is the slab. Now, ACI 318 has not been neglecting slab and continuity reinforcement for decades now. And what they essentially try to do is they develop a punching shear scenario. They worry about punching shear, and they develop mechanisms to hang the cast-in-place flat plate slab off the stump of the column where the punching shear occurred around the perimeter. Now, it's not really continuity reinforcement in a catenary membrane sense, but it's evolved into that very rapidly because it's titled integrity. Okay? Now, if you can rely on some form of membrane behavior in the steel system, you will get some definite benefits, at least in terms of its ability to resist disproportionate collapse. So what you see here is a two-dimensional membrane catenary behavior where the dimensions of the panel tend to dictate the response. So it's the old two-way slab theory, right? If it's a one-to-one panel, slab or load spans in two directions. As it migrates to a rectangular panel, there's a dominant direction in the response. Now the steel system unfortunately has a welded, or I should say a steel deck, and that's a unidirectional spanning entity. But as long as the damage coincides with its spanning capability, we might have something favorable. You can't always say that that's going to happen, but it's certainly there. The most important things to recognize during the response is anchorage and the capacity itself within the membrane. It's tension, right? The concrete slab is going along for the ride. It's what's inside and below the slab that's going to contribute to that robustness. Now, what this model allows you to do now is investigate local damage to the girders in the beams. Right? That's another aspect that's often overlooked, and it's something that we can begin to understand at least a little bit as we move forward. And that's what we'll look at now is those characteristics of the system when girders and beams are damaged. Now, a typical infill beam being lost, maybe it gets hit with a forklift, maybe it's a hit from any other kind of vehicle, who knows what it might be. Could be fire, right? Fire has been studying the membrane capacity and tensile capacity for quite some time. We don't take advantage of it in integrity, but it's there, and it's important. So if you lose the infill beam, this is very favorable because your steel deck is spanning in that direction. So you've got some tension reinforcement in the deck, provided you can anchor it, and you've got some membrane reinforcement in the form of welded wire mesh present as well. So those two things are going to begin to help you carry loading. Now, the studies that we had done looked at carrying a sustained loading, a point-in-time sustained loading of about 100 pounds per square foot on this slab. That's fairly good. There's no dynamic multiplication that can be carried, and the General Services Administration has some factors that are being discussed and being manipulated, but those factors essentially account for the dynamic change in the response of the system, and that essentially was omitted here and really couldn't be carried. But sustained loading likely could have. Now, the typical system does indeed have some levels of inherent robustness that we could count on, and then we migrated into a two infill beam scenario. So this is just walking around and doing what-if studies. So if you lose two beams, looks very punishing, right? But remember, the slab is going to want to span two directions. That's why you get flat plate cast-in-place structures that are 4 inches thick spanning 25 feet. Okay? There's economy there. And that's essentially what's being activated in this system. Now, unfortunately, the steel deck can only contribute in one of those two directions. So you don't get the bang for the buck that you might out of the welded wire fabric. Now, if you wanted to enhance the robustness of the system for these two scenarios, you obviously could lay mild steel reinforcement inside there. Okay, but again, this is looking only at the slab, not at the system at this point in time. So there's some more things that we're still omitting and neglecting. Now, what happens if you lose a spandrel beam? Now, that you've got no choice, right? One might argue that the steel deck is going to cantilever depending on this span. That's true. But if you were to look at generating a membrane, and some people have cabled the perimeter of buildings, etc., you could obviously lay in additional tension reinforcement along the perimeter of that panel and have everything move forward fairly well with that reinforcement. Now, if you lose a spandrel girder in this scenario, you're losing a lot of the framing system. Unfortunately, if it's a spandrel, you've lost all your anchorage out there as well. Perhaps. Okay? Now, in that particular case, one-way membranes might form, and you're going to have to span quite a long distance to get through there. Fortunately, if you have anchorage of the deck at these locations, you can span pretty far with steel deck. Okay? However, the magnitudes of the forces that are present out there are significant. It's not likely a puddle weld scenario is going to carry that. So what we had done in the analysis is we had defined an area of the steel deck that corresponded to the strength of the puddle welds. Okay, so we manipulated the deck area to get a membrane tension reinforcement that would be appropriate for what the anchorage is present at the ends. So these systems in these four scenarios allow us to point out, number one, we need to understand anchorage at the ends of these systems better. We need to understand what steel deck can do with these spans like this all by themselves. We need to understand what catenary and membrane reinforcement can be generated with welded wire mesh in these systems. And then the last thing that we need to do is, what does the steel system now do in 3 dimensions? And how can we put the two together? And there are people doing that with very high fidelity finite element models. But I tend to take the position I'm going to study with schematic things first, then I will begin to progress in the direction that we need to go, and that's what we essentially tried to do here. So we took a look at a 3-dimensional system with some end connections around the perimeter and in the infill beams. So each one of the squares that you see here is a 30 by 30 panel. And at the perimeter of the panel, you have connections that have both axial strength and stiffness, as well as moment strength and stiffness. And those are accommodated in this model using very, very short beam elements. Again, it's a model. Okay? At the ends of the girders you see here, there are also rotational strength and stiffness and axial strength and stiffness. Now, what you can do in inelastic analysis, and I used Mastan in this case. Unfortunately, I used a version of Mastan that did not allow you to warp the interaction diagrams and the yield surfaces, so I warped them myself in the way that I knew Mastan would do that. So what you see down here are some admitted simplifications of the axial load moment characteristics of the connections that you see here at the perimeter. Okay? They're not the strength of the member. There's something much less. And 3 systems were analyzed. Now, in order to figure out what the membrane was going to do, we loaded it with the distributed load of some magnitude. In this particular case, we got about 50 pounds per square foot that membrane could carry. And at the central location here, we got about 26 inches of vertical deformation. Now, if that's happening in the system during response to damage, you are going to drag the membrane concrete floor system down along with the steel grillage together. And dragging them down together makes compatible deformations happen, and as a result, superposition of the strengths could occur. Now, I'm not guaranteeing you're going to model the response exactly, but strength, you're going to do a reasonable job with that. So with those 3 systems, we can look at response. In the response of the 3 systems, and I was very glad to see Jesse Carnes and the MHP work previously to get some confidence that the flyer I was taking at the time with these responses has some basis in reality. It was gut feel at the time. I don't have a huge lab. We got a lab with a colleague here where we can do some testing. But the response that you see in System 1, you can start to see the transition from the flexural mechanism to the geometric stiffness. Now, that geometric stiffness can go on forever, right? We have the circus performers that walk on tightropes. all right, provided you can carry that loading. So at some point in time, the compatibility of deformation between the grillage and the membrane need to set the strength of the system. And that's essentially what's being done here. So that transition from flexural to geometric stiffness is important. I think it's more important to have it controlled as well and not rapid. So if you look at System 2, what we did here, and maybe I should step back a minute and focus on the connections that were present in this system. They're on what really is the low end of simple connections. If I jump back to that slide here, these are all simple infill connections. No WOOF-B connections, nothing of that nature. Okay? They're simple. What does the structure have out of the box is what we were trying to figure out. 5 minutes. Be almost done. In this particular case, we have a strength of the system that has moment strength that is higher than System 1 and axial strength that's a little higher. As we move forward here, the analysis is telling us there's a singularity. Okay, we have an instability. It's the analysis. The real system's not going to tell us that same thing. So what happens after the fact, we wanted to figure out, well, how do we relate that back to another system? And that's what we did here with System 2. We kept the moment capacity a little bit less than System 2, and we kept the axial strength in the connections the same. And as you do that, you get a little bit more controlled variation between the flexural mechanism and the catenary tension. More importantly, there's a controlled transition there, and we don't know what might be happening here. My gut tells me it's going to jump across over to here. I don't know how rapidly that'll occur, and I don't know what damage that might incur. Now, what we've done at MSOE with a colleague in the audience, Chris Rabel here, and some of his graduate students, is we did some connection tests, and we did 27 of them, 3, 4, 5-bolt simple connections. We did shear tabs, doing single connection angles, and doing WTs. Now, as you look at the response of these, there's 17 inches of deformation on a 14-inch span, and nothing's fractured yet. If you look at what's going on in the angles, you're flattening them, and you're actually pulling the angles off the bolt heads. Okay? You've got some limit states going on here, and these were just simple shear design connections, if you will. So that process is ongoing, and Adam Friedman, Scott Thompson, and Matt Johnson are doing some excellent work, and we're trying to figure out what's going on right now. Looking at the data, looking at the strain readings. Now, in summary, a steel system is inherently robust. We have to figure out how to let it tell us what it already knows, and we need to start digging at that information. Performance-based engineering might be a way for us to define a robust system, and it might also be a path for us defining a measurable level of integrity provisions, okay, so that we can have some targeted provisions for that kind of activity. The flexural mechanism superposition is a good way to go about assessing the characteristics of a robust system. And the in-plane stiffness of the floor system is important, and it likely plays a role in tying the system together. And it'd be nice to understand that. And then also, that membrane and catenary capacity of the system might be better off as a smooth transition from flexural to catenary. That's something we might need to look at more frequently and in more detail. Strong column, weak beam behavior is likely a good thing, and we knew that for quite some time. And then a robust system will also have some connections that are capable of undergoing full reversal of moment with axial loading. That's something we need to begin to study, and that's something we need to begin to understand a little bit better. 3D framing systems are another very important thing, and we need to understand this transition from flexural to catenary behavior. And in conclusion, I'd like to thank the AISC for some money to begin thinking about these things. Unfortunately, as you think about a project like this, you raise a million questions more than answers. Tom Schlafly, also the Committee on Research, a few presentations that I've made there to help formalize some thinking. Larry Kruth's in the audience, Joe Zona, a number of individuals on that committee. And finally, to all of you for the 8 o'clock in the morning attention. Thank you.
Stay right here.
Yep, I'll do that.
Questions? Yes, ma'am.
Yeah, the question's related to the shear tabs and whether or not AISC is going to begin to carry out some activities to allow more use of the shear tab connection. The axial capacity in those, there is some there. It's not a lot. As you start to migrate into three-dimensional behavior, I mean, we're usually doing the testing that you see here that's planar. Perpendicular to all those beams that you would see there if it was a girder line, there would be another, perhaps, 6 members connected in that would begin to help share some of that loading. Now, they are doing some testing. In fact, we're having a working lunch today to begin to formulate some processes for understanding connection behavior, much along the lines of what you're describing. Now, when we did our tests with Chris at MSOE, that was really what we were looking at, is what does the simple connection have inherently, and what can we rely upon? And there is something there. I agree with the economy. The axial load capacity, it's still being investigated.
Other questions? Yes, sir.
The question is related to the membrane capacity and how it can actually work within a real system. I would agree with many of the points that you're saying. The anchorage capacities at the ends of those particular panels are large. They're in the individual beams, as you saw in the skeleton type analysis, and they're also in all the puddle welds, headed studs, whatever are present at the perimeter of that panel. Now, I'm not saying you're going to be able to carry design level loads with these systems, but I think you can carry point-in-time sustained loading on the system with what's there naturally. And that's really what we're trying to understand a little bit more, is what can the structure carry on its own, and then we can begin to enhance it. Now, pulling the columns in, I agree with, but the problem is that column, in some cases, in many cases, is connected to other parts of the system that are going to resist that pull. Now, is that a good thing or a bad thing? Kind of depends, right? If the system can withstand the tension capacity that you're pulling with, then you're going to get a fracture perhaps if you continue to accumulate loading. If that system can carry it, then it's not a big deal. If the column will just pull in and you get a P delta type failure, that might occur. But what I like what you're saying in that you're thinking about a three-dimensional system in the response. That's what I think we need to start doing. We need to quit thinking about the normal two-member scenarios.
Well, the typical specification requirement I've seen has been design all simple shear connections for either the shear reaction or an axial force reaction. And I don't see how that can, the structure can't support it.
No, it's right.
If you're going to pull in on that spandrel column and depend on the slab to carry it, you damn well better have a horizontal shear capacity into the sides of the column.
Oh, you're going to have a lot of other mechanisms to get forces around. Now, Kirk is going to speak about some of the requirements that you're talking about at a much higher level than I am right now. It's very important. The forces that you saw in that catenary test in the beams were on the order of 50 kips.
50 kips I can
Okay, that's right.
But when I've got a member with a big beam with 500 kips.
I agree.
Real world frustrations are
Yes, I agree. It's very difficult for everybody here. You can't hear all the back and forth here. So when you ask a question, please be as succinct as possible.
or loud.
No, we have.
And we can talk later.
Chris will be very happy to discuss with you after the presentation here. But the input here is very critical, and we really, really appreciate your questions and your comments. Any more questions? One more question. Okay.
Thank you.
Thank you very much, Chris. Okay. Chris has mentioned the name Kirk to you several times. This is Kirk Marchand, who is managing principal of the company with the title Protection Engineering Consultants. It's a new line of work in consulting engineering, and Kirk's firm is one of the first. They're very busy, and they're dealing with some very tricky practical issues that affect all of us and how we build and service our structures. So Kirk's presentation, Guidance for Progressive Collapse Analysis.
Well, thank you, Radar, for the introduction. I'm not sure I'm going to speak at a higher level. First of all, I'm shorter than Chris, so definitely will speak at a lower level. I'm also from Central Texas, so I'm going to talk slower. It's also probably related to the fact that I'm not as smart as Chris is. I want to thank Chris for doing an excellent job in hitting a number of the issues related to understanding the robustness that we know exists in structural systems. Steel, in this case, is the topic du jour. it's a matter of quantifying that robustness and finding the points at which we depart from that, the points where we can count on things breaking and we know we don't need to go there in terms of counting on capacity. It was an excellent question about developing this these membrane forces and catenary forces, and it is a huge part of the problem. Years ago, when after the Ronan Point collapse, apartment building collapse in England, and the Brits came up with the idea that they needed to incorporate sort of enhanced integrity or tying provisions into their design guidance. They did that and assumed some mechanisms of membrane action and catenary action, which we have sort of stolen and begun to incorporate into some of the DOD and GSA guidance, which I'll talk about real briefly here before I get into the guts of the presentation. But the fact of the matter is, if you don't have anything to react a membrane force against, it's not going to go into membrane. And so you can think of a plan of a building that might be 5 bay by 5 bay, 10 stories tall. If you're expecting catenary action in many of the perimeter bays, and worst case, if you're expecting catenary action in the corner bay, forget it. It's probably not going to happen. So developing membrane action is one mechanism, but it's not the answer. Our firm has been, just to set this up a little bit, our firm has been working with others. Two of them are in the audience here, Jesse Carnes and David Houghton, on updating the Department of Defense guidance for what we call in this country progressive collapse, a better term which is used in Europe, and I think we're going to try to migrate our language here, is disproportionate collapse. And the topic that we're really addressing here is the fact that we don't want an action, as the Brits call it, or an event that is focused on a very localized part of the structure and damages a localized part of the structure. We don't want that to result in a widespread collapse of our structural system. So we don't want the response to be disproportionate to the initial load. Hence I like the term disproportionate collapse better than progressive. Progressive collapse implies that there's some sort of dynamic migration of collapse, and I don't think any of us necessarily believe that really occurs in all cases. So disproportionate collapse is what we're talking about. Back starting after the Murrow building collapse in Oklahoma City, the GSA developed some initial guidance for their buildings to try to incorporate some additional robustness into their structural systems. They started out by looking at reinforced concrete in detail. Jesse and David and their firm participated later in updating that original GSA guidance to put some good recommendations for steel. The Department of Defense had some initial guidance developed in the late 90s, which worked its way into some pretty detailed guidance. UFC, Unified Facilities Criteria, is what the Department of Defense calls it, 402303, methods to mitigate progressive collapse. And that document is now being upgraded, and the GSA guidance and the DOD guidance are being merged into an approach that, to be honest, will be the only sort of holistic approach that's documented in this country to look at methods to mitigate disproportionate collapse. That guidance is prescriptive in nature. There's some other terms that are thrown around for progressive collapse, and that's indirect design and direct design. Indirect design generally implies that you're doing something to the structure to enhance integrity, enhance robustness. Typically, in terms of the GSA and the DOD guidance, that's tie force provisions. That's including this extra steel to help develop catenary or membrane action. And then that document refers to direct design, which is trying to develop these enhanced flexural mechanisms at connections so that you can count on that in the event of loss of key member, columns, transfer girders, those sorts of things. In my mind, all of that is really prescriptive guidance, and it's good. And what will be in the updated DoD and GSA guidance will allow someone to use either the provisions of tying or the alternate path approach, developing of enhanced flexural mechanisms, to try to understand how we can make a structure better in terms of accommodating an initial level of damage. But it's all still prescriptive in nature because we're defining the initial level of damage. Basically, we say that one key element magically disappears, whether that's somebody running into it, somebody blowing it up with an explosive charge, construction defect, whatever. It is one element that disappears. So that's prescriptive in nature, in that we are prescribing the initial level of damage. Depending on how long I go here at the end, I'll talk to you about an effort that's ongoing within the Structural Engineering Institute to develop more general guidance, where practitioners, according to a level of risk, and Chris talked about the European approach of consequence categories. In this country, we're moving towards using occupancy, the occupancy tables from ASCE 7 to define sort of what your level of risk is and what corresponding action you should take. But ultimately in the SEI guidance, we hope to have some prescriptive approaches that you use if you don't know what the initial action is, you don't know what your specific threat is, but also to allow the practitioner, if he can do a risk and vulnerability assessment and define the problem, whether it's explosion or a train running into the building, taking out 2 columns, or potential construction defects, he can do more of a performance-based design. He can identify what's missing and then go through a structural analysis to improve the structure. So we're going to try to do both a prescriptive and a performance-based approach. But what I'm going to talk about today is Chris very eloquently described the idea that the connections that we deal with on a day-to-day basis have a lot more capability probably than we understand. We were hired by a group called the Defense Threat Reduction Agency, who sponsored a series of tests to look at steel connections under these types of scenarios. Single column loss, gravity loads then try to displace that double span condition. We were tasked with looking at the data they generated and sort of presenting it in the context of how it could be used to support the progressive disproportionate collapse guidance that's out there. These tests, and I won't talk a whole lot about the whole series of tests, but I'll introduce them a little bit. Defense Threat Reduction Agency is DTRA. They did a series of, or a test program of 4 series, 4 phases. The first phase, they looked at connections of columns at base plates, those sorts of things, to blast loads. Phase 2, they looked at the response of the member itself, the column itself, under blast loading. Phase 3, they developed a structural system with beams, girders, and the column, and blast loaded that. And Phase 4 then, which is really what I'm going to focus on today, is the ram load test, where once that column is damaged and essentially removed from the structural system and you push down on it, what do we have left? How do those connections perform? And so the intent of the program that DTRA sponsored was really to understand at a top level how blast fits into this equation. When you do the analysis, the GSA approach or the DoD approach, the key element removal is what I call the immaculate removal approach. And that's the column basically just vanishes. We don't say how it vanishes. We don't say there's any other consequences to it vanishing. It just vanishes. Well, clearly for DOD, they're thinking about a terrorist threat. So they're thinking that there's a car bomb or a satchel charge or something. Well, the question has always been in the back of a number of our heads, what additional things are going on, mechanisms are going on here by the initiating action, by the explosive action, which is really the 800-pound gorilla in the room with DOD. That's the threat. And so DTRA sponsored this series of tests to investigate that and say, well, if we damage these things with blast and then evaluate the capacity, do we see a difference? So the Phase 4 test looked at some that were blast loaded, others that were pristine, that would better replicate the immaculate removal approach. Well, this is the series of tests, and this gives you an idea for Phase 3 and Phase 4 what tests were performed. I'm a blast guy, not a steel detailer or designer, so this is the terminology that DTRA used in the test. Seismic moment connection really is essentially the wolf flange, the welded flange connection, bolted. Wind moment is essentially just a bolted cover plate connection. Then they evaluated bolted shear tab connections and bolted split T connections. Most of these were tested in Phase 3, which means that there was an explosive event that loaded the column up and caused deformation in the system. Rotation of the column, rotation of the beams. But some of them were just Phase 4 tests, and that's where the same system was built. The column was just cut off, and then the ram force was used to push down. Well, this is let's see, Chris, did you leave your... Oh, okay, thank you. This is the structural setup that was used, and essentially there's sort of a column bay right here in the center. This is essentially the double span beam that we're testing, and these are the connections of interest right here, adjacent to the column. So very stiff and significant anchorage on the end here that would represent a lot of bays of structure on the other side of this bay that was damaged that are providing that axial capacity in this member. So this is held on to pretty well. In the Phase 3 tests, this was all covered with cladding. So there was a charge that was out in front of this structure, out here somewhere. This was all covered with cladding, a column in the middle here. Blast goes off, blast load loads all this up, destroys the cladding, but in the process loads up this column, generating the damage in the column and then potentially the damage up here in the connection area. This kind of gives you a little bit of a top view of that. The measurement system here, there was a ram that's pushing down on top of this area where the connections are, where the column was before it was either blast damaged or removed. Strain gauges in the beams, load pins out here at the support, so we can actually measure that axial force as it's generated. Here's a picture of a blowed up, a post-blast condition. Use a technical term, a blowed up column. Again, Central Texas creeping in there. Tested member. So there was cladding here. The kinds of loads that we're generating with these explosions are very significant to get the kind of damage that we want. And again, this was a specific type of scenario. So this would represent the outside of a building, the perimeter bay of a building. The charge that's sitting out here would be something akin to a vehicle bomb, not somebody placing 50 or 75 pounds directly against this column. This was more of a uniform load, if you can call it that. It's applied to this system. As the cladding responds and breaks apart it dumps load into that column, generating the damage you see, but also generating some of the rotation and torsion and damage as you see up here, the idea being that we wanted to represent that in these tests, just to be able to compare or get a sense of how blast damage compares to non-blast damage, again going back to the immaculate removal.
What kind of connection was in that middle column that has the great deformation?
The connection, you're talking about at the base?
No, the beam to column connections at the topwards twisted.
Yeah, he's asking what type of connection this specific picture is. I don't know, Jesse, you may be able to help me. It looks like I don't think there's a that's a woof, right? I don't think there's a cover plate on there. That's the woof connection, right? So it's bolted and welded there at the flanges. And obviously this is a pretty healthy base plate too that didn't fail. So, but a couple of things are interesting about this, not directly related to this talk, but if you start pushing down on this after you've deformed this column to this point, we're all trained that there's no capacity left in that system, right? Because of, P delta and everything else. There's a lot of capacity left in that column. And so that's one interesting thing you begin to learn from these. We discount. We say, look at the damage in that column and there's nothing left. Well, there's something left. I mean, there might be as much as 30% of the vertical load carrying capability that there was when you started. So that's not insignificant. So a lot of interesting things learned in here. All right, so what we were asked to do was to review the data for the tests of a number of these connections, to try to come up with a scheme to compare them in terms of the rotational capacity, flexural capacity, and then energy absorption from a flexural standpoint and an axial standpoint. Chris talked about that transition from flexural to axial, and that's a real important point that we tried to get a handle on here. We were tasked with saying, well, okay, how can you implement these results into the existing GSA DoD criteria, which is essentially swiped from the FEMA 356, now ASCE 41 approach, where it is essentially a flexure-based approach where you're given some allowable rotations to work with, depending on your connection type within ASCE 41, and so that is what the updated GSA DoD criteria will refer, even more so than in the past. It will refer you back to ASCE 41 and how you do your analysis. So the thinking here was, as much as we could use this data to refine that approach, that would be our ultimate goal. Knowing that there was also this axial stiffness, geometric stiffness, if you will, that Chris referred to, that comes into play. So that was what we were tasked to do. The measurement scheme or the evaluation scheme we came up with was to look at ductility of the different kinds of connections and compare them in terms of rotation. And then we came up with a scheme for comparing them on an absorbed energy basis, which I think is a kind of neat way to look at one connection with respect to the other. One of the parameters that Chris mentioned that you need to consider in an alternate path analysis, or this sort of flexural analysis, highly inelastic behavior of these connections, is this dynamic increase factor. And he alluded to that as sort of the inertial resistance that the system offers, and the dynamic increase associated with the fact that this is not a static loading; it's a dynamic loading. Well, we've looked at that in the process of developing the updated DoD GSA guidelines. In the existing guidelines out there, it makes you double the load. It says, well, it's a dynamic system, so worst case would be if it stayed elastic and you multiply your load by 2. Well, clearly, if we're going to allow significant inelastic behavior of these connections, 2 is very conservative. And so we've gone through the process now in the new UFC. Well, you'll as a function of the inelasticity that your connection allows, you'll be able to back out what multiplier you have to put on load. And generally speaking, you're not going to have to increase your load more than 20% in any case. So we're dropping down now from a factor of 2 to a factor of 1.2, which is very significant. And so we did that based on a number of analyses of three-dimensional structural systems, including different levels of inelastic behavior. But generally speaking, you're never going to have to increase your load more than about 20% over the actual load. So that's an interesting conclusion there. Axial energy we looked at as a percentage of total, again comparing that geometric related energy to flexural. And then finally, one of the things we looked at after we noticed some differences in the data with what you would get if you used the ASC 41 modeling procedures is and Chris again alluded to this, is the stiffness that's actually present in these connections, which generally, based on this data, is less than what you would assume creating that modeling curve based on ASC 41. We compared the results to the life safety, and again, this is sort of the inelastic behavior limits that you're allowed to use in ASC 41. There's life safety, and this is seismic-based. Life safety, collapse prevention, and these are the definitions of those. Generally speaking, you know, the UFC and GSA guidance leans towards allowing this collapse prevention value. We're talking about extraordinary loads here. And then we compared the stiffness, as I mentioned, from ASC 41. All right, well, let me go through some examples of these, the performance of these connections. And basically what we were able to generate from each of these tests, remember we had strain gauges, we had load pins, and then we had the ram force, and then we had a measurement of deflection for each of those connections. And so there's several things you can generate here. And the first, sort of in the upper left, you can simply plot as a function of chord rotation. That's another way of expressing deflection. The force, the ram force that you're applying to the system to generate the displacement, and you can compare that with the axial force that you would measure directly from the load pins or that you would infer from the strain gauges. And so we plotted that for each of the tests. There's some difference in what you get out of the strain gauges and what you get out of the load pins. Generally, we believe the load pins in all of the tests. But what was reassuring was the strain gauges were at least giving us about the same shape there as things came apart. But as I run through these, I'll show this every time because this is the one that's sort of the mechanism of how things pop and break. We've plotted that on there. In the upper right, what you can do based on a little sum of forces calculation is you can actually plot what we call a shear force or a force related to flexure in the system. You can plot an axial force and a total force. And if you add those two together, if you add the axial force together and the shear force together, you should get the total force. You can compare that to the ram force. And lo and behold, there's actually two plots laid up right on top of one another there, and you do get that number. Well, once you know the shear force, then you can actually calculate a moment, since you know the distance from the pin over to the deflection point where you got the ram force. You can actually plot then moment versus chord rotation. And then if you make an assumption about the extension of the beam, in other words, as I push down on that beam, if my ends are restrained and they're not moving in, I'm stretching those beams. And so I can calculate an amount of energy per rotation. And a couple things this allows you to do. First, this allows you to kind of look at the flexural response all by itself. And then this allows you to look at that transition that Chris talked about, when you go from flexural energy to axial energy, and allows you to compare then for the different types of connections how much of the connection performance is being supplied flexually or axially. And a real simple-minded, which means me, approach to this would say that ASCE 41 approaches, generally we're assuming flexural response of this system. We're not assuming a substantial contribution of axial energy. So if and as we've plotted here, the other thing that's on here is the life safety value, the collapse prevention value, and then this proposed, which is sort of a rule of thumb, it's 80% of what we saw the transition from flexure to axial be. As long as these points are down here in the region where the contribution of axial energy is relatively small, then the assumption that doing this analysis just based on flexure, albeit at fairly large rotations now, which absorbs a lot of energy as this thing tries to drop, is still a fairly reasonable assumption. The other nice thing is if this is our performance value here, and I've still got these plots going a long ways out here, I've got a significant amount of capacity left in these connections, and so if I define my performance value sort of at the hairy edge of, or 80% of this observed flexural capacity, I've still got a pretty good safety factor because I've got a good bit of capacity left in that connection due to geometric stiffness. But the thing to keep in mind, well, some might say, well, okay, then why don't we just put the allowable rotations out here? Well, part of the reason is this transition from flexural to geometric is not happy. It is not a pretty situation when you transition from flexural. You got a significant load, a drop in load, and generally speaking, in our dynamic analysis, we don't, we assume a nice, pleasant transition from one to the other. So there's some dynamic things going on there that we might need to worry about. So we're happy just to evaluate these out to this point. And so for each of these connections, I've kind of plotted those, at least 3 of those, in some detail. And for example, that first one we looked at, this is the seismic moment. And I might mention that some of these tests had a slab in place, some didn't. This happens to be a blast tested one, and we'll look at connections that were not blast tested. So this is slab present blast tested. And so you can kind of march through here and see where the different events took place that gradually degrade the performance. So we've got bottom flange and bolt failure there, second bolt failure there, third bolt failure, and then top flange failure. So you can kind of see how the events take place in the degradation of this connection. I talked about calculating that shear value, which allows us to essentially evaluate the moment versus deformation and that flexural energy, and that's simply based on, as this angle changes as I displace this, then the sum of forces suggested that more of the force goes into axial response than was in the shear response. So that's all that was done there. And this is that plot that was in the upper right-hand corner that kind of shows you flexural force, axial force, and then the sum of the two for that particular connection. Have that shear value, you can calculate the moment versus rotation, and of course the squiggly lines are always the actual. The red lines in these plots are if you use the stiffness from the guidance in ASC 41, this is the kind of modeling curve that you could develop. Well, as you can notice, there's a significant difference there. If I pick this point as my allowable, the area under this guy for the actual is a good bit less than the area under that whole thing. So that stiffness is a big thing that we're thinking that we might need to take account of in future guidance. Change in length, simply a geometric calculation. And then finally, as I said, if you consider that change in length, you can compare then the flexural energy there, or work, and the axial work, add those two together, and you get the total work that's being done by the ram over the displaced element. And then you can kind of compare the life safety value, the collapse prevention value, and sort of our proposed value, 80% of loss of flexural capacity. And again, these are significant rotations. That's something to keep in mind here. So that was for essentially the Wolf connection, blast loaded with a slab. This is no slab, no blast loading, Same connection. I'll just kind of pop through these a little bit. This would be the sort of sequence of events, and not very much different, really. Bottom flange first bolt, second, third bolt, and top flange failure. Thing that's interesting, though, is in a non-blast loaded case, if you plot this moment versus rotation, we're doing a lot better as compared with the modeled value. So clearly, blast affected the performance of that WOOF connection in terms of the available energy, if you will. And if you compared this to the previous plot, that's essentially what you would see. So here's a comparison. Good bit of flexural energy that tapers off down here at the values we're proposing. Small amount of axial energy that then takes off at larger rotation. So this says that for non-blast loaded cases that the guidance that's in ASC 41 and hence the UFC is pretty okay. So marching through these, just to compare, this is the cover plate connection, no slab, blast loaded, sequence of events here, bottom flange failure, web tear, angle failure out here to basically 12% significant rotations. This connection behaved really strangely in these tests. This is the blast loaded case. So here's your predicted, your modeled flexural moment versus rotation. This is the tested value. So significant difference there. So again, based on the modeling curve, the energy you would expect versus rotation versus what we actually saw in that blast loaded test. If you go to the no blast loading on the cover plate connection, kind of a different animal. It looks like what you would expect. So again, the modeling curve from ASC 41 and the results of the test, except for the fact that this guy tails off pretty good here at the end, this does pretty well. So there's some strange things going on with the cover plate that make us suspicious of how well it performs. That's the energy comparison for the no blast load. Side plate, Jesse and David can talk about this a lot more and better than I can, but same sort of approach was used, comparing. The interesting thing with the side plate is because of the significant rotations you can get, had to stop and install a spacer so you continue to push on the thing and get as much rotation as you wanted out of it. But the modeling curve that one would expect and the nice performance of that connection. The values out here, and there was a little bit of difference between the I guess proposed collapse prevention value and sort of 80% of what was the apparent flexural response. So that's one thing we noted in the report and in the study. And then again, this is a plot of the energy. And what's interesting, if you remember the cover plate connection, out here at the range where we've got the suggested performance values, there's a significant portion of the available energy that's contributed axially for this type of connection as compared with, say, the cover plate and some of the other ones. So this is something to think about in terms of the total. Here you've got almost 50% of the energy is related to that geometric response. So that says you're doing that modeling. You may want to consider that when you do that. Side plate, no blast loading. A little bit of an interesting response there. There was a little bit of buckling going on here at some point, but the connection did recover. So with respect to the modeling curve, maybe this area equals that area, and you're fine. But that was sort of an interesting observed response there. And there's a picture of the buckling that occurred. Well, when you compare all these, what is it that you can discern? Well, you can compare it based on total absorbed energy. You can compare them based on percentage of axial energy. You can look at these from a stiffness perspective to decide what it is we should improve. And then you can evaluate the sensitivity of these to blast loading or without blast loading. Instead of ranking of connections, this should probably say performance comparisons of connections. And so basically what was done was we looked at the FEMA 356 ASC 41 values for collapse prevention, and then what will likely be proposed in the 2008 Unified Facilities criteria. And so we do that for rotation, for ductility alone, for energy, and for percentage of axial energy. So there's a series of plots here which I'll go through quickly, but it just kind of shows you in terms of the rotation available, moving from the bolted split T here over to the left to the shear tab connection here on the right. And what should jump out at you here is that shear tab connection is a partially restrained connection, but it has significant ductility, so it's not going to come apart on you as you're counting on these other connections to provide capacity. And oh, by the way, that connection also has some capacity in terms of energy. You may have a lot of shear tab connections in your structure for gravity beams or whatever else, and so this is not an insignificant conclusion. You may have a lot of energy there that you can count on available to help you out. Sensitivity to blast loading, you can compare each of these, cover plate, blast loaded, no blast loading. This was the oddball where the difference between blast loaded, no blast loading. I'm sorry, these actually line up correctly. You'd expect for no blast loading to get better performance in terms of rotation. Absorbed energy, total absorbed energy, you can rank those again comparing to ASC 41 FEMA 356. So again, bolted shear tab on the left, and I should mention these are total values and minimum values. Obviously side plate's the big winner here. Cover plate connection, seismic moment, bolted shear tab. So there's based on a comparison based on the total energy, sensitivity to blast loading. You can compare each of these with blast loading, without blast loading. Not a whole lot of difference in the seismic moment. Some difference in side plate, significant difference in the cover plate. And then axial absorbed energy is important just from an analysis standpoint. Are we going to allow guys to continue to kind of do this just flexurally based approach? And so you can compare, again, the percentage of energy, and as you would expect, side plate's pretty high over here, but the bolted split T is also. So that's something to consider when we develop further analysis guidelines, that it's significant out at the ranges we're proposing for the acceptable performance criteria. That guy has a significant portion of its capacity due to the geometric stiffness. Sensitivity to blast loading, the cover plate connection, this is the one that's kind of flipped around for cover plate. So you can compare both of these in terms of blast loaded or non-blast loaded in terms of axial energy. This is the oddball of the bunch here. Connection stiffness. We tried to evaluate that from each of the tests and compare that to the modeling stiffness. And you can plot sort of the percentage of the design stiffness for each of the connections. Around 100% for the fully restrained would be an ideal value. So when these values are a little bit lower, we need to think about how we're recommending modeling stiffness if we're just using flexure as an analysis approach. So finally, what can we do with all this? Well, we think we can use it to validate ASCE 41 criteria for the collapse prevention values that we'd like to use. Maybe in the future bump some of those values up a little bit. It gives us a little bit of confidence that the flexural approach that we're using is reasonable. We've got a significant amount of capacity beyond the flexural mechanism in these connections. That's kind of our safety factor. There's some conclusions here that are arguable, and Jesse and David would probably argue about, but there were some things we saw in the test for all of the connections, particularly the cover plate, the unpredictability of that. It gives us pause as to what we recommend the performance criteria to be. No strong correlation. There's a limited number of tests, but as far as with and without slabs on beams, whether or not that should be a big contributor. Energy absorption, small difference for seismic moment connection, large difference for the cover plate, as we saw. Sensitivity to blast loading, it was really there in all cases, and that's something for us to think about. It may be that in future recommendations for the analysis that we say, if you're evaluating the connection that's right there where the blast occurred, you should probably degrade the allowable performance of those connections. At floors above there, you may be able to use the ASC 41 collapse prevention values. So that's kind of the thinking that we're going towards there. Stiffness, I think, is a significant conclusion from these tests, that we probably need to adjust the modeling stiffness that's allowed if we're going to stick with the ASC 41 approach. So we can use the data. We can consider the blast-loaded cases probably worst-case scenario. The overall case was worst case because these were exterior columns, and it was an overall sort of vehicle bomb type blast loading. Satchel charge, you'd have shearing or base plate failure, but probably not near the damage up at the top of the column in terms of the interface between the beams and the column. So may adjust the performance criteria based on damage and decrease the FEMA modeling stiffness. And that's it. May I answer any questions?
A lot of things to think about here for everybody. Questions? Yes, sir. Succinct questions.
Did you test any dog bones?
No, I don't think we did. Were any dog? No. There was talk at some point.
There was a large scoop of
Yeah.
that were slated to be testing, but of course funding always seems to lag behind.
Right. Yeah. And I don't think it's completely off the table. I mean, the test structure is still there, and so if somebody comes up with some money, maybe there will be. But the question was, were there other types of connections, specifically dog bone, investigated, and not at this point.
Yes, sir.
Oh. What David said was that I only presented sort of our review of the experimental results in terms of comparing these to ASCE 41 approaches. There was a significant amount of other work done. David and his firm did some significant analysis that also included some of these other connection types. There was also a numerical modeling part of this study from modeling the blast all the way forward through the response of these connections dynamically. And if you want to go ahead and start a run on a multiprocessor machine and wait about 14 days, those work. But we could actually do the test quicker than those numerical analyses. So there was a question there.
Okay, the David that Kirk refers to is David Houghton of Side Plate Systems. Just so you know, he's sitting over there if you have any questions for him. Question here. Yes, ma'am.
The question was that one approach folks will use to incorporate robustness, if you will, in these structures is to simply, even though you may not have the seismic requirements, but to impose those requirements to say that, well, that's bound to incorporate a significant amount of additional robustness into the structure. Several points to that. One, the reason for using ASCE 41 was not so much to say that there's an equivalency between disproportionate collapse and a seismic event. It's that the analysis procedures that were available in ASCE 41 were very applicable to this. So that's the first point. people miss that point, but that's a very important point to make. Second, there certainly are aspects of the seismic provisions that will make our buildings more robust with respect to these types of events. Do we need to specify the full range of seismic requirements? No, I think clearly we don't. There are some provisions that we need to acknowledge that are important and we should incorporate, but the mistake I think that people make is saying that there is an equivalency, and so let's just impose all of the seismic requirements and we're bound to be better. Well, we're probably somewhat better, but we're also bound to be much more expensive. So the intent of this study and the intent of the emerging guidelines presently incorporated in DoD and GSA and emerging hopefully over the next couple of years in the SEI work that we're also involved in will be to allow the practitioner, the structural engineer, to do this analysis on a conventional system. In other words, he can take these more conventional connections and evaluate their performance from a highly inelastic, nonlinear perspective and get a sense that, yes, my structural system does have a significant amount of capacity for this type of event.
Okay. Thank you, Kirk. No more questions. If you want to ask questions, Kirk and Chris will be available after the session, of course. This session repeats tomorrow afternoon at 3:30 here in this same location. But join me in thanking our speakers again and for all the questions and comments.